All right, hello, hello. Dr. Pitcher here, and in this lecture we'll be taking a look at Lewis acids and bases. And I have the definitions here. You probably remember them from one of the earlier lecture videos, but I'll just go over them again. Lewis acids are electron pair receptors or acceptors. Let me call that acceptors. Sorry. And Lewis bases are electron pair donors. So it's analogous, but kind of the reverse of the situation with Bronsted acids and bases. A Bronsted acid is a proton donor. A proton is a positive charge, and electrons are negative. So donating positive charge is kind of equivalent to accepting negative charges. So the Lewis definitions just broaden and expand what we can consider acids and bases. So another term that we'll use is electrophile for Lewis acids. And another term that we will use for Lewis bases is nucleophile. And we can take a look at, say, maybe some examples. It's probably the best way to look at things. And let's start with, I'm actually going to start with Lewis bases. So Lewis bases, or nucleophiles, and these Lewis bases are going to feature extra electron density, or we can say that they are electron rich. These could be things that have lone pairs. And just as an example of that, we could have something like OH minus, NH3, even something like Cl minus. All right, so we know OH minus is a good Bronsted base. It's also a good Lewis base. Cl minus is a very weak Bronsted base, but it's actually a reasonable Lewis base. It's got a bunch of extra electron density. There's actually 4 lone pairs. It's relatively electron rich. We could have things that have pi electrons. We'll say pi systems. And these could be things like carbon-carbon double bonds. So pi electrons can react. So if our pi system comes across something that's electron deficient, then we can get a reaction. Yes, these are a few examples, and we'll run across more of them later on. And in particular, we will actually start using the terminology nucleophile instead of Lewis base when we talk about Lewis bases later on. So you'll see a bunch of this actually in chapter 6, and then again in 7 and 8 and 9 and 10 and 11. And anyway, you're going to see nucleophiles and electrophiles over and over. So let's take a look at if these are our Lewis bases, let's see what we have as far as Lewis acids are concerned. And again, these are electrophiles. And these are electron deficient. So they are species that have less electron density than otherwise. And so examples could be empty p orbitals, or let's just say incomplete octets. That's probably the better way to describe it. And those are things like, oh, we could have boron, we could have carbon, and let's do, I don't know, I'm going to put some CH3s there just to make things a little different. Positive charge on that carbon. Both of these are essentially the same electronically, that we've only got 2, 4, 6 valence electrons. 2, 4, 6 valence electrons there. So we have our, we don't have a complete octet, so that's our incomplete octet. So, you know, sometimes we can have metals. So something like, I don't know, Fe, Fe, let's see, FeCl3 would be one. So we'll just do FeCl3, AlCl3. So again, we could have things like carbocations, boron, we can have metals. Because metals are electropositive, that is, they're not electronegative, they tend to have less electron density on them when they're bonded to electronegative atoms. So those metal atoms are going to be electron deficient. The other case that we can have is we could have polar bonds. And an example of this would be the carbonyl. So let's just say we had acetone here. And so this bond, the carbon-oxygen bond, is polarized. Okay, the oxygen's more electronegative, so it pulls electron density towards itself. So we have delta minus, partial negative charge on the oxygen, and delta plus, partial positive charge on the carbon. So now that carbon is electron poor, or electron deficient. Okay, it's got that partial charge. And we can see this with other types of bonds, bonds between carbon and halogens, like a carbon-chlorine bond, you know, and certain other types of bonds, bonds like so. All right, so let me think if there was anything else I wanted to say about the, oh, you know, there's actually one more type of Lewis base that I wanted to mention, and this is and that is, you know, with our Lewis acids, we have these polar bonds that are, you know, another example here again is, say, a carbon-chlorine, delta minus, delta plus. What if we had carbon bonded to something that was much less electronegative than carbon? So oxygen's more electronegative than carbon. So yeah, carbon's going to be electron deficient. What if we had, say, a carbon that was bonded to something like lithium? Now, lithium is very low on the electronegativity scale, so in this case, our bond polarization is going towards the carbon. So now I've got a partial negative charge on the carbon and then a partial positive charge on the lithium. So this basically functions like a carbanion, like having a lone pair and a negative charge there. So, this pair of electrons can do a Lewis acid base reaction pretty readily. Okay, so just wanted to mention there was another type of polarity to mention there. All right, so anyway, let's take a look then at some Lewis acid base reactions. And these are examples of what we call polar reactions. Where typically we'll have something that is, partially negative and something partially positive, or maybe entirely negative and entirely positive. So let's just look at some examples here. So we could have, let's see here. Let's do this. Let's do this guy. So I've got my trans 2-butene, and I'm going to react it with HBr. And I can draw some arrows for my electrons, just like I did with in resonance structures. And we'll use them to represent our flow of electrons as new bonds form. So I could have something like this, where my extra electron density in my my nucleophile pulls off, in this case it reacts with this hydrogen here, which is going to be the electrophile. And in my product here, I'm going to end up with a positive charge and then my Br minus has a negative charge. So my charges are conserved, that's good. But now I have my nucleophile reacted with my electrophile to make a new bond. So that's one feature with Lewis acids and bases, is when your Lewis base reacts with your Lewis acid, when your nucleophile reacts with your electrophile, you form a new covalent bond. Now notice that in this intermediate product here, I've got a carbocation. That's going to be an electrophile. And my bromine has lots of electron density on it, negative charge, 4 lone pairs, so that's going to be my nucleophile. And now I can draw my arrow showing where my electrons are going. So they're flowing from the bromine, so we start them at the lone pair, and they end at that carbon nucleus, the electrophile. And then that gives us our final product here. And now we've got our 2-bromobutane. So this is an example of a Lewis acid-base reaction. In this case, we have a Lewis acid that also happens to be a Bronsted acid. HBr is a good Bronsted acid. So our Lewis base is reacting with something that's both a Lewis acid and a Bronsted acid. But this Lewis base is not a Bronsted base. This normally won't pick up it picks up a proton here, but you know, a lot of times we don't think of double bonds as being bases, okay? But yet, in the Lewis definition, they can be, and they can undergo this type of reaction. One more example could be something like, let's say we had NH3, and we react that with, let's see, what should I do here? We'll just do a carbocation, why not? So we'll do CH, CH3, CH3, positive charge. So now my lone pairs, or my lone pair rather, there's just the one lone pair, can attack that carbon, and I'll end up getting HNHH, new bond C, H, CH3, CH3. So this is my nucleophile, and this was my electrophile. And then I end up with a positive charge in my product on the nitrogen. Remember, your charges should always balance when you're looking at or writing chemical reactions, chemical equations. So I could draw a bunch more of these examples. I'm not going to, but I do want you to practice identifying types, or identifying Lewis bases, identifying Lewis acids. And again, just to summarize, what should you be looking for? Well, for Lewis acids, you want to look for things that are electron deficient. So incomplete octets, metals with electronegative things attached to them, FeCl3, AlCl3, FeBr3, or polar bonds, carbon bonded to something electronegative, like carbon-oxygen double bond, carbon-halogen single bond. Those are going to be Lewis acids. Protons are also, let me add that in here. So H plus, because that has an incomplete, well, duet in this case, because it's the duet rule for hydrogen, not the octet rule. So those are Lewis acids. To back up a little bit further here, our Lewis bases, we want things that have that extra electron density. They're electron rich. So things with lone pairs. Things with lone pairs can be Lewis bases. Pi systems, those can be Lewis bases. And then certain kinds of polar carbon-metal bonds where the electron density is more on the carbon than on the metal. So it's the opposite of our CCl bond, where the electron density is on the chlorine. So our carbon is electron poor. Here, the electron density is on the carbon. Lithium's electron poor, but this extra electron density, that can react. So when you're looking and trying to identify in practice problems, when you're trying to identify Lewis acids and bases, those are the things to look for. So Lewis bases, look for lone pairs, look for some double bonds, or pi systems, but they should be carbon-carbon double bonds. Okay, carbon-oxygen double bond, because it's polar, is going to be a Lewis acid. So yeah, Lewis bases, look for the extra electron density. Lewis acids, look for electron deficiency. All right. Well, that is about all I'm going to say right now for Lewis acids and bases. We'll go ahead and talk more about Lewis acids and bases, electrophiles and nucleophiles later on in the semester. So until then, stay safe. Bye now.